Hey guys, welcome back to Google Chem Tutoring. I'm Austin. I'll be running through part 2 of problem set 20, intermolecular forces. Number 5 says, assuming each of the following are pure liquids for which is hydrogen bonding the dominant intermolecular force. Okay, so if you remember back when we were covering intermolecular forces here, hydrogen bonding is where a hydrogen is bound to N or O or F, and then that's interacting with another N or F on a different molecule, okay? So let's see where that could be true. Well, first of all, let's look for where hydrogen is bound to N or F. So here I've got hydrogen bound to an O, okay? And what they're assuming is that this is interacting with itself, so don't get confused. So if I have another guy like this and it looks like this, okay, then yeah, I do, don't I? I have this hydrogen interacting with this oxygen here, or vice versa on the other side. Yeah, that's going to be that's going to be one of them that has hydrogen bonding as the dominant intermolecular force. Okay, so that is an example of hydrogen bonding. Part B says difluoromethane. Okay, well, I have hydrogen, but it's not bound to an N or F, right? F is here, but it's not bound to N or F. Okay, so that's a big difference here, because this will be a nonpolar bond. Okay, that's the biggest difference. So in this case, we're not, even though we're next to a fluorine, we're not bound to the fluorine. So this is not going to have hydrogen bonding. Phosphine, okay, hydrogens here aren't bound to N or F, so yeah, no, that's not going to be it either. Now, hydrogen peroxide, here we are bound to an O, right? And then let's say I'm interacting with another N, O, or F. Okay, well, another hydrogen peroxide, I mean. Okay, yeah, here's my hydrogen bond right there. Yeah, those can totally interact on both sides, right? Okay, now acetone. Earlier we talked about acetone interacting with water, but now we're talking about it interacting with itself. And if you look, hydrogen is not bound to an oxygen here. Sure, there are 3 of them bound to this carbon here and on the other side as well, right? But it's not bound to the oxygen. And so the dominant intermolecular force here is dipole-dipole, right? That would be the strongest intermolecular force. But it does not have hydrogen bonding because the hydrogen is not explicitly bound to the oxygen. So let me circle D here really quick just to make it obvious of which ones are hydrogen bonding. Okay, letter F, last one, pentanal. Well, we've got hydrogen and we've got oxygen, but they're not bound together, right? The hydrogen is not on the oxygen. And so this is not going to have intermolecular forces when it comes in contact with another pentanal. So that's not going to be hydrogen bonding either. So if we look at all the options, it looks like just A and D are going to be hydrogen bonding just based off the criteria of what makes up a hydrogen bond. Okay, number 6, in an aqueous solution containing Na+, Mg2+, K+, and Ca2 salts, which do you expect to experience the strongest ion-dipole interactions? Why? Okay, so important to note here is you're going to have to use a law that we've used previously, but that maybe you don't remember quite what like that you had to use it for this situation. So it's called Coulomb's law, okay, and it looks a little bit like this, okay. It's the proportion of the charge of one compound times the charge of the other over the distance between them, and technically the distance is squared, but we'll just call distance r, okay. So in this situation, what you're looking for is the highest the highest number of Coulomb force. So the way that you do that is, first of all, you look at the charge that it has, okay? First, the charge that something has. So in this case, I'm going to write in a plus for Q1, and then we'll just say the minus is coming from water, and we'll say it's consistent for all these, right? Because water, even though it doesn't have a full charge, it does have quite a strong dipole, right? It's got a hydrogen bond, right? So we'll just say it's a full minus just for simplicity's sake. And then and we'll just put that over R. So this is going to be 1 over R, okay? And it'll be negative 1 over R technically. So that would be for Na+. Now, I'll show you how to compare that to the rest of these here, and we'll see how to rank these. So then let's look at Mg2+. Well, Mg2+, we got a 2+ right here, okay? And that would make it negative 2 over R for Mg2+. Remember, this is just a vague way of representing Coulomb's law right here. Okay, so this negative 1 over R, it's not a real thing. It's just negative. It's just saying here's the charge, okay, and then there's the distance between them. So just bear with me, and I'll show you what this should look like here in a second. So K plus is going to look like Na plus, but we'll see how it differs here from it in a second. So K plus is also negative 1 over R, and then Ca2 plus is going to look like a lot like magnesium because it's got also a 2+ charge. So that's going to be Ca2 plus. Now, you may be asking, well, how would I rank these in terms of strongest ion-dipole interactions? Well, the strongest ion-dipole interactions are the strongest Coulomb forces. Now, maybe I didn't explain very well, but the Coulomb force, what it represents is the attraction between two charges, okay, or two molecules with different charges, or if they were the same charge, the strength of the repulsion between them. And so the closer, let's say, a negative and a positive are to each other, the stronger the Coulomb force, but the further away they are, the weaker the Coulomb force, okay? So that's what we're looking at here. And in this case, we're looking at how would the cations here, okay, compared to the water, okay? How do they interact with the water? And the strongest one is going to be the one with the highest charge and the smallest distance. So if I were to rank these, I would first look at the weakest ones. Okay, so I would look at these first as the weaker intermolecular forces, because charge will take precedence over distance every day. So I'll rank these Na plus and K plus first. Now K plus is a lot bigger than Na plus on the periodic table because it's one period down from it, right? So its distance is a lot bigger. Okay, a lot bigger, and so because it's bigger, this overall Coulomb force is smaller, and so I would rank K plus as the weakest intermolecular force, or the weakest ion-dipole interaction. And then I would have, actually, let me just put these in terms of K plus, and then less than, and then it would be Na plus just by default because it's the next biggest without increasing in charge. Okay, and then between magnesium and this calcium here, magnesium is smaller, okay, which means the radius, the distance here is smaller, which makes this number a lot bigger than the one on calcium. And so I'd put calcium here and then Mg2 plus here. So when you're doing this, you're looking at really at first their charge, and then their size if the charges are the same. If the charges are not the same, or if the charges, if the charges aren't the same, then just go based off charge because that'll take precedence every day. But if they're the same charge, then you'll have to look at their size. And so in this case, we're going to say Mg2 plus, both because of its size and its charge. We'll just put size and charge. Now, size being the fact that it's the smallest, okay? And that's what we're really going for here. Okay, so when we're looking at something like that, especially with ion-dipole questions, you're likely going to have to use Coulomb forces for that and for ionic bonds to determine the strength between the two molecules. All right, last one. Number 7, tetrafluoroethylene C2F4 is the molecule from which Teflon is made. Okay, A says draw the Lewis structure for C2F4. Okay, so first of all, I'm going to assume that carbon are the two center atoms because they can make the most bonds. So I'm going to make a bond between them, and then I'm going to attach them to fluorines on both sides, and I'll assume that they're both attached to 2 and see if it works out. Okay, if I do that, then the only thing that I'm missing is probably a double bond here, just because of the extra electrons that carbon has, and they're not being used to make other bonds. So I'm going to assume that that's a double bond. So that would be the Lewis structure for this. And if you can imagine, this is flat. Okay, this is flat on a plane because both of these are trigonal planar, and then they're double bound here, which locks them in place. So they're not rotating around any bond. So these are perfectly symmetrical, okay? So in terms of does it contain polar bonds, it does contain polar bonds because the electronegative difference between fluorine and carbon is greater than what, 0.5, right? It's greater than 0.5. Pretty much anything bound to fluorine is going to have an electronegativity difference of greater than 0.5. And so the bonds are polar, but and so I would draw the dipole moments here, here, and there, but when it's asking if C2F4 is polar or nonpolar, I'm going to have to say nonpolar because the vectors of each of these dipoles cancel out, right? One's going this way, one's going that way, so it's perfectly symmetrical. All right, so it says D, what is the steric number of each carbon? Well, carbon, if I redraw this here just to reiterate here, it's bound to 1 carbon, right? 1 carbon. So that's one steric number, 2 fluorine, 1 fluorine, and another fluorine. So that's a steric number of 3. Okay, it's a steric number of 3. So without any lone pairs on the central atom, the bond angles of this trigonal planar formation is 120 degrees. Okay, 120 degrees. So that that is something. If you don't remember a lot about VSCPR and stuff like that, I would go back and review those to make sure that you can get these kinds of questions. Okay, F says state the hybridization of the 2 carbon atoms in C2F4. Well, if my steric number is 3, I don't even need to look at the rest of the structure. I know that they're both going to be sp2, okay? sp2, because I needed one s. I needed, a steric number told me I needed 3 orbitals to hybridize, and I have available to me one s and 3 different p orbitals. And I need 3 total, so I'd take an s and 2 p's to make that. And then I'm left with this unhybridized p orbital, which actually is what makes my double bond here. So this is going to be sp2 hybridized. G says Teflon is formed when a C2F2 is polymerized, or in other words, when the pi bonding electrons are used to form sigma bonds between molecules, linking many C2F4 molecules together in a long chain of polymer, as shown to the right. Okay, what intermolecular forces do you think dominate in Teflon? Well, Teflon is, if you remember what we just said, it's non-polar, right? These are all canceling each other out. And so even though these bonds are polar, the intermolecular force is actually London dispersion. Now, you may be like confused because we just said that London dispersion was the weakest of the intermolecular forces. However, because London dispersion forces are in every molecule, the bigger the molecule, right? Teflon can be gigantic. It can be like tens of thousands of carbons long. That gives the reason when we were talking about London dispersion forces in terms of size, right? We said that in comparison to helium, I2 was definitely had stronger London dispersion forces because of what? Because of its size, right? And the bigger the chain polymer gets, the bigger the electron cloud gets, and that makes it way stronger in terms of intermolecular forces. And in fact, these types of London dispersion forces can get to be even stronger than some ionic forces. It gets really insane. Like if you heard, like PVC pipe is very similar to this, right? PVC is just polyvinyl chloride. Okay, it's just a bunch of chlorides in a huge long chain of polymers. So, anyway, Teflon is super strong, not because of dipole forces or hydrogen bonding or even ionic forces, but simply because of London dispersion forces that get bigger as your molecule gets bigger. Okay, all right. So H says, do you think Teflon should be hydrophobic or hydrophilic? Well, we just said it was non-polar, right? And so it wouldn't likely interact with polar substances, which makes it hydrophobic. So I'm going to say hydrophobic because it's a non-polar monomer that just gets polymerized and it maintains its non-polar character. Okay. All right, last one. I says, why do you think Teflon forms such an effective non-stick surface for cooking food? Well, most food is polar, right? Most things, most food has a little bit of water in it as well, and so they're very they're very hydrophilic. But if you're working with Teflon, it serves a very good non-stick surface because it's so hydrophobic. It's not gonna let the food stick to it all that well, and so because of its non-polar character, it's actually very good at keeping stuff off of it, especially polar substances, of which our food is made up of a lot. Okay. All right, so that'll finish it up for intermolecular forces. I know that's a lot of information, and I know there was a lot of steps maybe that you didn't know you had to go through, like Coulomb forces or going through shapes, right, and drawing Lewis structures. But if you need a refresher on that, I really suggest that you go back and watch those videos and get a refresher on those, because those will largely determine answers and answers to questions both on your homework and on the test in the future.